I hope everyone is doing very good. Let's continue the chapter called electromagnetic induction, right? What was the chapter we are discussing? Electromagnetic induction. In this, recently we had finished the concept called self-induction and energy stored in an inductor. What is that? Energy stored in an inductor. We had finished recently these two topics. Now, when these inductors are connected in series and in parallel, let's look at what is the effective value of the inductance. Alright, inductance. Inductance is denoted with the symbol L. Write this. You might have recollected by this time. Self-inductance is denoted with the symbol L, and this is also called as coefficient of self-induction. What is that? This L is also called coefficient of self-induction. What is this? Coefficient of self-induction. Alright. Now, imagine I have two inductors which are connected in series. You can see here. This is my plug key here, and the net EMF of the circuit is E, and EMF induced here is E1, EMF induced here is E2, right? So here L1 is the self-inductance of the first coil, L2 is the self-inductance of the second coil, right? Now, here what you should understand. And before moving to this, let me tell you one important thing. Inductor is analogous to resistor, yes or no? I've told you clearly in the last class. Resistor will oppose the current. Simple. Inductor also will oppose, but see here, inductor also will oppose, but it opposes the change of current. It opposes what? The change of current. So that's the main difference, my dear children. Inductor will oppose the change of current, resistor will oppose the current. That's it. So here there is a concept of resistors can be used here. When two resistors are connected in series combination, what happens? The potential drop across this plus the potential drop across this is equal to net potential of the circuit. Yes or no? Same thing I am writing here. E is equal to E1 plus E2. And the effective inductance, same like effective resistance. Effective resistance in this case, when they are connected in series, R1 plus R2 is the effective resistance here. Effective inductance will be L1 plus L2. That's it. These two things you should remember. And in parallel combination, let's see in parallel combination what happens. So similarly, so there is an inductor of induced EMF E1 and inductance L1. So here also there is another inductor of EMF E2 and inductance L2. They are connected in parallel, right? See, this is the key and this is the net EMF EC. So here positive terminal, negative terminal, definitely there will be current I1 and I2. Current will split into two, similar to resistor's case. Here what I can write, total current is equal to the sum of the current which is moving in different branches here, right? So I1 plus I2. This is according to Kirchhoff's first law also. Okay. After that, when two resistors are connected in parallel, you know how to find the effective resistance. Similarly here, so L effective inductance is equal to L1 L2 by L1 plus L2. This is also the formula you should remember. Alright. Here comes the concept called mutual induction. What is that? Mutual induction. Mutual induction, self-induction is done. Now it's mutual induction. Self-induction means there is only single coil. See, for example, this is the coil we have considered only single coil and discussed about self-induction. How the induced EMF is produced due to its own magnetic field and magnetic flux change. That's called the self. Here, mutual inductions means, as its name indicates, there must be two. Mutual means two. Two. What are those two? That is two coils. What is that? That's two coils. And let me give you a simple and easy example to understand mutual induction. Imagine I have a coil here where there is a galvanometer is kept here. There is another coil which is kept very close to it. So there is another coil which is kept very close to it, very close. So this is the plug key K, and the potential of this battery is V in the positive terminal, negative terminal. Now what I am going to do here is very simple. When the key is closed, simple, I am just closing the key. What happens here? When I close the key, the current will start flowing in it. Yes or no? Current will start flowing in it. When current passing through it, there will be a magnetic field associated around this coil. Yes or no? This magnetic field will pass through this coil. When these two coils are kept very close, and listen, it's so simple. Imagine in this coil there is a current passing through it, and surrounding of this, you know how the magnetic field will be produced, right? At the center of the coil, the magnetic field produced will be, so mu naught I by 2R. If the radius of the coil is R, mu naught I by 2R. If there is only one turn, this is the magnetic field at the center of the coil. Clear? Now, this is the coil in which current is passing through it. It will definitely associate a magnetic field, and that magnetic field lines will be passing through this coil. Understand? When it is kept very close. If this current is changing, right? That's what my point here. If the current is increasing, what happens? If the current is increasing, the magnetic field associated with this coil increases. So more number of magnetic field line passes through this coil, second coil. So second coil will be having a magnetic flux change, right? So magnetic flux change. So I'm writing here, current is increasing in the first coil. So this is the first coil. I'm writing it as a coil called primary coil and denoting with the symbol P. What is that P here? Primary coil, in which the main current is passing through it, right? So I is increasing in the first coil. Because of this, there is a magnetic flux change is linked with the second coil. The magnetic flux change is linked with the second coil. And second coil, I am writing it as S. So where S is secondary coil. Due to the current flowing through the primary coil, there is a magnetic flux linked in the secondary coil. So due to this magnetic flux change, so there is an induced EMF develops. In where? In second coil only. Due to this induced EMF, there is an induced current also produces, alright, in the second coil. It's so simple. Mutual induction is the phenomenon of, see, I'm writing the definition from here. It's a phenomenon of producing induced EMF in a secondary coil, due to the change in current with time passing through primary coil. Passing through where? Primary coil. That's called the mutual induction. And that's it. So simple, right? So phenomenon of producing induced EMF in a secondary coil due to the change in current with time passing through the primary coil. So simple. Okay. Now, look at here. We know the magnetic flux linked with the secondary coil is directly proportional to current passing through the primary coil. This I am writing, if there are n number of turns, I am writing here n into magnetic flux linked with the secondary coil, which is equal to, there is a constant, and that constant is equal to m here into IP. What is that m? So that m is coefficient of mutual induction. Here itself I am writing here, you can see m is coefficient of mutual induction. So coefficient of self-induction is denoted with the symbol L. Coefficient of mutual induction is denoted with the symbol M. Or it's also called as mutual inductance. What is that? And M also represents the mutual inductance. Alright. So mutual inductance also represented with the symbol M. Now, here this M, you can write the expression here. M is equal to N into phi S divided by IP. So remember this M expression. And this mutual induction SI unit is also called Henry, alright, denoted with the symbol capital H. Simple. It is also Henry, and mutual self-inductance formula also, unit also Henry. And this mutual inductance is depending on, as you can see, the geometry of the coil and the distance between the coil, number of the turns, right? On all these factors, the mutual inductance depends. And most importantly, mutual inductance is also depending on the orientation of the coils. Imagine I have one coil here, another coil here. Both the axes are parallel. Understand? So this is called the axis of the coil. This is the axis of the coil. You have one coil here, so imagine this is the axis of the coil. Okay. When two coils are kept like this, when their axes are parallel, I can say the angle, understand? So the axes are parallel, I can say the mutual inductance is maximum. Okay. So I am saying here, angle or axis are parallel, M maximum we obtain. Mutual inductance value is maximum. So whereas these axes are perpendicular, for example, this is one coil and this is another coil. You can see one axis is like this. So this is another coil, right? So its axis will be like this, right? So one coil is like this. So another coil is like this axis. So one coil axis is like this, another coil axis is like this. In this case, so when axes are perpendicular, so what happened? So there is a minimum of mutual inductance will takes place. Okay. So this is how, what are the factors affecting the mutual inductance value also, right? So let us discuss now with the more details of mutual inductions. Now we are going to do. So what we had just derived, number of turns into a magnetic flux linked with a secondary coil is equal to coefficient of mutual induction, right, or mutual inductance into current passing through the primary coil. All right. From here, we know the formula E is equal to minus d phi by dt, where magnetic flux change that is connected with the secondary coil only. So this I can also write it as minus d by dt of, so if you take the number of turns are 1, so then that will be m into I suffix p. So finally E is equal to minus m into dIp by dt. So this is the induced EMF produced due to the mutual inductance. Right? Induced EMF will be produced in secondary coil or the coil which is kept very close to the primary one. So this is the induced EMF produced in the secondary coil due to mutual induction and due to current passing through the primary coil. Now the question is, mutual induction in a long solenoid, right? In a long solenoids, I can say, a long solenoid kept coaxially. Mutual induction in long solenoids kept coaxially. Let me draw a solenoid here, air core solenoid. What is this? Air core solenoid. So simple topic. Imagine a current I1 is passing through this. This is the solenoid S1 with a number of turns N1 and the length of the solenoid, I can say number of turns per unit length N1. So I can also write small n1 is equal to number of turns per unit length. Area of cross section is A. Area of cross section is A. I hope you are understanding the situation here, what I am considering. This is the axis of the solenoid, yes or no? Coaxially, and one more thing, and before moving to the next solenoid, before drawing the next solenoid, I just wanted to tell you here, magnetic field associated with this solenoid will be mu naught number of turns per unit length into current passing through this. Current passing through this is I1. Alright. So mu naught number of turns per unit length in this I can write N1 by L into I1. Okay. Mu naught Ni. So this is what the magnetic field associated to this one. So now the interesting part will come. Mutual inductance means there must be two coils, right? This is only one. So now the second coil I am just going to draw here, my dear students, and look at here. This is the second coil. Carefully see. This is the second coil. Almost of same length and same area of cross section. Almost of same length and same area of cross section I have taken. Almost. So length is same. And area of cross section also same I had considered, and there is a number of turns in this is what the second solenoid, number of turns in this case is L, and here I can write small n2 is equal to capital N2 by L, number of turns per unit length in second coil. Now the concept is about mutual induction, right? About the second, so I can write here. Carefully look at here, my dear students. Magnetic flux associated or the linked with the second coil is equal to, what is the formula? N into B into A. Here comes point. What is N? Number of turns in the secondary coil in which magnetic flux is linked now. Magnetic flux change is linked now. B is magnetic field due to the first one. Understand? So this first one will produce magnetic field and that only will create a magnetic flux change linked with the second coil. So this is what the magnetic field due to the first one. Now this is area of the secondary coil, because flux is linked with the area of the secondary coil. So here, if I substitute all the values here, N2 into, so B1, what is B1 here? Mu naught N1 I1 by L. So mu naught N1 I1 by L into area of cross section. So magnetic flux linked with the secondary coil is mu naught N1 N2 A by L into I1. Right? What is our aim? Our aim is to find the mutual induction or mutual inductance. Right? What is our aim? To find a mutual inductance, my dear students. Mutual inductance is denoted with the symbol M. How can you find M from this equation? I'll tell you the important and easy thing. The easiest thing to find M from here is, let us compare this equation with this equation, my dear students. Imagine the number of turns in the secondary coil is not taken. Right? What is that? Phi S is directly proportional to I1 or IP. So phi S is equal to M into IP. So what is this M? See. Magnetic flux linked with the secondary coil is equal to, so M value into I1. Alright. Clear? The basic equation. So magnetic flux linked with the secondary coil is equal to mutual inductance into I1. It's fine. It's done. So this is your mutual inductance value. Right? This is your mutual inductance value. So what is your mutual inductance value from here? So let's write here mutual inductance in case of the long solenoid mu naught N1 N2 A by L. I'll tell you one more important thing here. Listen. This is the expression. I can also write phi 2 is equal to, listen, M12 into I1. Right? This is M12. What is M12? You know, let me write this M12. Mutual inductance. Right? Mutual inductance when current is passing through, the first coil. See, one indicates mutual inductance when current is passing through the first coil, and flux change is linked with the second coil. That's called M12. What is that called? M12. So you can also do in this way. Imagine current is passing through the second coil initially, right? Current is passing through the second coil. So in that case, flux is linked with the first coil. So here also can do the same. So the same expression, I can also write it as when flux is linked with the first coil. Okay. So now this mutual inductance when current is passing through the second coil and the flux is linked with the first coil into current passing through the second coil. Okay, so current is passing through the second coil. Let us name it as I2. So this is also true. So here also you get the similar equation, right? So here also you get M21 is equal to mu naught N2 N1 A by L. You get the similar equation. So you see this and you see this. Both the equations are correct, right? So I can say M12 is equal to M21, which is equal to mutual inductance of two long solenoids, coaxial long solenoids, which is equal to mu naught N1 N2 A by L. So very important formula is this one, right? So most of the times there were questions in JEE exam and NEET exam based on this formula. Try to remember the formula and try to write it in your formula book even. So mu naught N1 N2 A by L, right? Mutual inductance. Okay, clear? So that's it. Now, Sometimes the questions will be asked like this. There is a case 1. So there are two simple cases. You try to remember this. So this is, sorry, before moving to that, listen. Here, there is an inductor of inductance L1. There is another inductor which is kept very close to it of inductance L2. When current is passing through that, and definitely there is a flux linked in this case, so there is a mutual induction production, right? So that mutual induction in this case is equal to square root L1 into L2. Remember, my dear students, here. So this is the maximum value of mutual induction. Maximum value of mutual induction, because they are kept very close and maximum flux change is linked in the secondary coil. So if you consider it is a primary coil, it is a secondary coil. You can see here, so both are kept in this way. And they are not kept in this way. Listen. When you keep the two inductors in this way, maximum flux will not be linked in the secondary coil. If you consider it is primary coil, it is secondary coil. It is 100% sure that maximum flux will never be linked with the secondary coil. Yes or no? Because of what? Maximum, because of they are not kept close by and they are not kept aside. Okay? There's a lot of difference between keeping here and keeping here. So maximum flux will be linked here. So that's your value here. And in these cases, maximum flux will never be linked, but there is a mutual induction, right? Some amount of flux will be linked through this coil, and that mutual induction is equal to some k value into square root L1 into L2, where k value is less than or equal to 1. K value is lesser than equal to 1. And see here, and this is the k value is called coefficient of coupling. What is it? Coefficient of coupling, or it is also called as coupling constant. What is this? Coupling constant. Understand? Clear? So this is how some kind of numericals can be asked from these formulas. Maximum flux linked, maximum mutual induction, and here mutual inductions when they are separated in these ways, when there is no maximum flux linked. Okay? Clear? So this is how questions also can be asked. Here two important formulas we have discussed. When they give the coupling constant, use this formula to find the relation among mutual inductance, self-inductance of first coil and self-inductance of second coil. Right? If they give k value, if they have not given k value, that means you need to use this formula m is equal to square root L1 into L2. And this formula we have discussed, the most important formula, mu naught N1 N2 A by L. Clear? And let's discuss some more questions and topics. Alright, my dear students, and let's have a look at the numericals based on mutual inductance. Number 1. If the current in the primary coil is reduced from 3 amperes to 0, what is the change in current here? It's clear, the change in current is 3 amperes. In time, see the dt is also given 0.001 seconds. Induced EMF in the secondary coil, induced EMF is also given. Now this is E. Okay, calculate the mutual inductance between two coils. So mutual inductance, so if you take its magnitude, E is equal to M into di by dt. From here, E value is how much? 1500 is equal to M into di. It's 3 divided by dt, 0.001. From here M you can find out easily, right? So 1500 into 0.001 is equal to 3m. See here, 1 0 cancel, point will come here. Another 0, point will come here. So 15 into 0.1 divided by 3 is equal to m. From here, it's 3 5s. 5 into 0.1 is 0.5. So what we need to find? M value in Henry. Okay. What is the answer? What is the answer here? 0.5 Henry. This way numericals you need to solve. So simple, right? Now, a solenoid of length 50 centimeters. Look at here. A solenoid of length 50 centimeters. So the length is 50 centimeters. I can write 50 into 10 raised to minus 2 meter with 20 turns per centimeter. What is that? 20 turns per centimeter. See here. 20 turns per 1 centimeter. Total length is how much? 50 centimeters. How many total number of turns? That is what? Total number of turns in the first solenoid will be how much when it is length is 50 centimeters. Alright. So can I say that total number of turns here will be 20 into 50? Right? It is 1000 turns. Understand? Is it simple? Now, and the area of cross section here, A1 is equal to 40 into 10 raised to minus 4 meter square because it is given in centimeter square. It's completely surrounds. This is the solenoid is surrounds another coaxial solenoid of same length. Length is same in the second case. And the area of cross section, let me say area of cross section is 25 into 10 raised to minus 4 meter square with 25 turns per centimeters. Total length is same 50 centimeters. Okay, but it is 25 turns. Here the same thing here. 20 turns per centimeter. Total number of turns for 50 centimeters. Here, how many turns here? 25 turns per centimeter, that we write here, 25 turns per centimeter. So, how many number of turns per 50 centimeters? It is just 25 into 50. So, total number of turns in the second case is 1250, 1250. Okay. Now, calculate the mutual inductance of the system. So, what is the mutual inductance of the system? M is equal to mu naught N1, N2 by N1, N2, A by L. Here comes an important point, my dear students. Here comes an important point. Mu naught value, 4 pi into 10 raised to minus 7 into N1 also you have 1000. N2 also you have 1250 into, here comes A. What is A? Whereas two areas of cross section is given. One is A1 is there and A2 is also there. Which area you need to take? If length and area of cross sections are same, it is alright. There is no problem at all. But here, lengths are same but area of cross section is different. So when area of cross sections are different, inner coil, whatever is there, the inner coil you need to take it. Right? This is the area of the inner coil you need to consider. If lengths are also unequal, the longer, that means the primary solenoid length, whatever is given, that you need to take it. Understand? Clear? Now, this is area of the inner one. So, this is what the inner one. It's a 25 into 10 raised to minus 4 divided by length of the solenoid. Anyway, length is same here. So, it is a 50 into 10 raised to minus 2. Right? Any confusions here? Right? If lengths are unequal, you need to take the longer solenoid length. Clear? First thing, longer solenoid length. Number 2, if areas are unequal, you need to take inner solenoid area. Alright? If it is given as, this is the iron bar, on this iron bar, a solenoid is wound. In that case, it will never be mu naught, right? In that case, it will never be mu naught. So, it will be M is equal to mu N1, N2, A by L. And this mu, I can write it as mu R into mu naught N1, N2, A by L. Remember, this is the case we discussed for air core. Sometimes, this is an additional case I have told you. Sometimes it may not be air core. The solenoid may wound on the iron core. In that case, this is the formula, right? Here, they'll give mu R, relative permeability value. Okay, keep it aside. And if you solve this, you'll get this answer. 7.84 into 10 raised to minus 3 Henry. If you have doubt, you can check it. Okay? Clear? Let's see the last question here. Two concentric circular coils, one of small radius R1 and other of large radius R2, where R1 is far lesser than R2. So what does it mean? So here let me draw the diagram. So imagine a small radius R1 is here, small radius R1, and the another coil of huge radius R2. So imagine this is a coil R2 through which the current passing here. Imagine that current. So let me say placed coaxially with their centers coinciding, obtain the mutual induction of the system. Imagine the current I2 is passing through this, current I2 is passing through this, current I2 is passing through this. What is the magnetic field due to this I2 at the center? So that is called B2, right? B2 is equal to mu naught I2 by 2R2. Can I write like that? Mu naught I by 2R, right? Magnetic field due to a circular coil at the center. Mu naught I2 by 2R2. Now, because of this magnetic field, there is a flux change linked with this inner coil. So that's what magnetic flux linked with the first coil is equal to, right? Is equal to, what is that? So magnetic field linked with the second coil, magnetic field due to the second coil into area of cross section of the first one. Area of cross, this is the first one and the second one. Okay. In this area only flux change is linked, right? That is what. The flux change is due to which magnetic field? Magnetic field due to the outer one. Outer one is the second coil. Okay. Now, magnetic flux linked here will be B2. B2 is mu naught I2 by 2R2 into A1. A1 is pi R1 square. Okay. A1 is pi R1 square. So here what I can write, mu naught pi R1 square divided by 2R2 into I2. So that is phi 1, right? So can I say it is a mutual induction? Phi is equal to m into IP, right? So phi s is equal to m into IP. This is called a mutual inductance. See, this is the mutual inductance, right? Now, let me give you a classwork, my dear students. Here, classwork. It's simple classwork. Same. There is a square loop is placed, square loop whose side length is A. It is placed in a circular coil. Okay, in a circle. So here current I is flowing. The radius of this is R, radius of this circle is R. Now the question, so simple, right? Current I is flowing in this direction, Now the question is, what is the mutual inductance of the system? So that's it. What is the mutual inductance of the system? In this way also questions will be asked. Be ready for that. Okay? Clear? And let's solve, let's discuss one more concept today. Alright, my dear students. Now, the last topic, which is the introduction for our next session, is AC generator. We'll be discussing about this in detail in the next class. I just wanted to introduce this topic to you now. What is AC? It's alternating current. What is this AC? Alternating current. And this generator, which generates electricity from mechanical energy, right? So generator will generate electrical energy from mechanical energy. The first scientist observed the phenomenon and created this device, AC generator, is Tesla, Nikola Tesla, right? Now, here A rough diagram related to the AC generator, let me show you. So there is an U-shaped magnet here where the magnetic field lines moving in this way. So this is a rectangular coil where one end is longer, the another end is shorter, and this shorter end is connected to one ring and the longer end is connected to another ring, right? This is the introduction only. So we are going to discuss only the introduction. The in detailed analysis we will be learning in the next class. Just introduction. So this is one ring and this is another ring, and both the rings are connected to a galvanometer. Why? Because of the rotation of the coil. So rotation of the coil will be taking place about this axis. Because of this rotation of the coil, there is an induced EMF is produced in the coil, right? What is that? Induced EMF is produced in the coil because of rotation. Because magnetic field lines are constant here, you can see here. Coil will have its area vector and the magnetic field lines are like this, you can see, right? So depends on this, there is a induced EMF is produced. Why induced EMF is produced? Before that you know the concept, right? When there is a change in magnetic flux, as this coil is rotating, there is a magnetic flux change linked with the coil. When there is a magnetic flux change, there is an induced EMF is produced. That induced EMF in this case is variable. What is that? Variable. As long as the rotation of the coil is taking place, induced EMF will be produced, right? So here that induced EMF is equal to E naught sine omega t, right? Sine omega t. And what is sine omega t here? So this omega t here, actually this omega t is theta only. Omega is angular velocity, which is equal to angular displacement by time, right? So this is E naught sine omega t. You know how it will be? Listen, this is the alternating current graph. So this is induced EMF and this is time. Alternating current graph here. So this is like this. This is called one complete cycle of alternating current. So this is 0 and here this value is called peak value, that's called E naught, right? What is this? It's a peak value, E naught. And this is another peak in the opposite direction, that's called minus E naught. And we will be discussing about this graph and the details of alternating current generator in the next class. But now you need this expression to be remembered. So then the next class will be very easy for us. So this is E is equal to E naught sine omega t graph. Alternating current you can see here. So the current values are changing. Current values are increasing and decreasing. That means become 0 also, you can see. The current value became 0 also. Again increasing in the opposite direction and again became 0. So this is called alternating current. Direct current graph will be like this. See here. So this is EMF and this is time. This is the direct current. See, direct current is, there is no variation in their EMF or voltage. This is what? The voltage is keep on changing with time, because this is the induced EMF is a function of time here. You can clearly see. From where this expression we have got, that also will derive. Right? Clear? And depends on the orientation of the coil. Orientation of the coil, you can keep the coil in this way or in this way initially, right? In this way or in this way. Depends on the orientation of the coil. We may get the induced EMF versus time graph in this way also, my dear students, and no confusions at all. In this case, it's called the peak value, right? So this is called minus peak value, no confusions. But here, induced EMF expression will be E naught cos omega t. Right? Why it is cos and why it is sine, we might have discussed, we might have learned in the chapter called simple harmonic motion. But anyway, so look at these expressions. So when these expressions are divided with the resistance of the coil, so E by R is I, E naught by R is I naught into sine omega t. See the current value, this is called alternating current. I naught is the peak value of current, and here also if you divide this with the resistance of the coil here, so then E by R is I is equal to E naught by R is I naught into cos omega t. Okay, alright, clear? So that's it. So let us discuss about AC generator in detail in our next session. All the very best and get ready for your assignment. Thank you so much.